All right, welcome to podcast 12.3. And what we're going to do is focus on this thing right here, the ideal gas law. Super, super important. And what we're going to do, and this kind of piggybacks a lot on the KM theory that we looked at, we want to think about what an ideal gas is. And if you look at this definition right here, it's an imaginary gas whose particles are infinitely small and do not interact with each other. If you remember our KM theory, okay, we had that as part of the theory. These small particles, points, and they're not interacting with each other. We're going to assume this because it's going to make our calculations a lot easier. The values we get with our calculations are very close to what you would get anyways, and so we just got to keep that in the back of our mind when we're working these out. Now, there's a couple things that we want to also remember. For example, we are making the assumption that gases don't condense to a liquid at a low temperature, and I'm here to tell you that if you were to take a gas and cool it down, you would eventually get a liquid, and therefore we can't do gas law problems when it's a liquid, and so at low temperatures it doesn't really hold. We also assume, again, exactly like KM theory, that they're not attracted to each other and that they have no volume. So just something to think about when we're doing this. All right. Now we can take Charles' law, Gay-Lussac's law, Boyle's law, Avogadro's law, and we can combine it into one nice formula, my favorite formula, which I call PivNert. It's helped me remember it in college, and I've used it ever since. PV equals nRT. I will also show you how to kind of derive these from PivNert later, but we're not going to worry about them right now. But this equation right here, this is it. This is my favorite equation. I love doing gas law problems with it. This is the one. So we're going to work with that today, and we're just going to practice doing problems using that equation. And then my last bullet right here, the important thing is, it kind of goes back to the low temperature thing, but we also want to think about gases at high pressure. If I take a gas, and let's say it's in a cylinder, and I've got a piston, and I squish it, squish, I'm bringing the molecules close together, and they'll eventually coalesce into a liquid. So now, again, we don't have a gas, we have a liquid, and therefore we can't do gas problems with the liquid. So two things to remember, and this is very, very important. I want you to make sure that you know when gases are not ideal. Okay? And that's under those two conditions. High pressures and low temperatures. So, with that, let's move on to our first problem. I've got an example here. And I know some of your math teachers just have you use the PV equals nRT. They have you substitute right there and then do the math. I like rearranging the equations, as you guys know. So we're finding pressure. So the first thing I'm going to do is rearrange this equation. And pressure equals nRT over V. And again, I got that just by dividing both sides by V, right? You guys know that stuff, okay? So we've got that. Right? And so once I have this, now it's just a matter of me plugging the numbers, and I think the math gets a lot easier. So I'm running out of room, so let me do it over here. P is going to equal, the number of moles is 5.00 moles. Okay. R is 8.314 liters dot kPa over mole dot Kelvin, and then my temperature is 25, but it's not really 25, it's 298 K, right? And then last but not least, that's over the volume, which in this case is 20.0 liters. Okay, so now my pressure is going to equal 600. And check this with your calculator, 619 kPa, right? Now, I want to focus just quickly on this beast of a unit for the gas constant, okay? Because that thing tells us what everything has to be in. For example, we've got to have liters, right? Well, as you know, we'll probably give you milliliters sometimes. kPa, well, you might get millimeters of mercury, PA, torr, atmospheres. You got to put it in that one, all right? And then moles, we're going to have things in moles, and of course, as you know, you have gas. When we do gas sols, we always do it in Kelvin, all right? So let's just make sure these units cancel. I've got a mole here, got moles there, those cancel. I've got a K on the top, K on the bottom, that cancels. I've got a liter on the bottom, liter on top, that cancels. So there you have it. The only unit that's left is kPa, and you're done, okay? Now this brings me back to this other gas constant. I grew up with atmospheres. We still use atmospheres in AP class, and it's still used in a lot of college textbooks. So we're going to use both gas constants. It really doesn't matter which one you use, as long as whatever pressure unit you have is in the pressure unit of the gas constant. Your textbook uses 8.314, and so if you feel like always using that, do so. I will go back and forth because that's how I learned. All right. So with that, let's try another one. Okay. So we've got this stuff here, and we want to find. Look at this. We want to find how many moles. Okay. So I'm going to take my PV equals nRT, and to get moles over here, I'm going to divide both sides by RT. Right. RT. And that cross cancels, right? So now I have N equals, and my pressure in this case is 0.899 atmospheres. Okay. My volume is 425 milliliters. But what's the problem with that? Look at the unit for our gas constant. It's in liters. So I got to convert that. All right? So I know there are 1,000 milliliters in 1 liter, okay? Or move the decimal 3 places, either way. So that gives me 0.425 liters, okay? And then R, in this case, since I'm using atmospheres up here, 0.0821. I'm going to write out this unit, liter dot ATM over Kelvin dot moles, and that is times my temperature, which is not 24 degrees Celsius, but 297 K. All right. So use your calculator, double check me, but when you do that, you should get 0.0159. And let's look at our units. Okay. Atmospheres is there. Atmospheres is there. Liters is there. Liters is there. K is here. K is here. You've got the moles on the bottom of a bottom, so that's the reciprocal, which gives you that many moles. All right? So there's that problem. All right, how does it look? What I want you to do on this next one is give it a try and then see if you get the right answer. Pause the video right now. Try it out. Okay, let's see how you did. So I've got PivNert, PV equals nRT, okay, and I'm solving for P, okay, so I'm dividing both sides by V, right, that cancels there, and so P equals nRT over V. So now let's plug the numbers in, all right, so I've got 5 moles of CO2, 5.00 moles. My gas constant is 0.0821 liter dot ATM over K dot MOL. And that is times the temperature, which is 50 degrees Celsius, plus 273 is 323 K. And all that divided by the volume, which in this case is 125 liters. Okay? So when you do that, the pressure that we get for this one is 1.06. And again, if we just look at our units on the bottom, or on the top, on the bottom, liters on the bottom, liters on top, K on top, K on bottom, we have atmospheres. So 1.06 ATM, right? Did you get that? Okay, hope you did. Well, again, I've got two more. Try this problem. What I want you to do right now, pause the video, okay? Give this problem a try and see if you get it. All right. Hopefully you got the volume equals 23.0 liters. Now, maybe some of you are saying at this time, whoa, I got like 45-ish. Okay, well, let me show you probably where you went wrong. Okay, first of all, we're trying to find the volume, so V equals nRT over P, right? And so now I'm going to plug in my moles. Oh, wait, I don't have moles. I have 42 grams of nitrogen, 42.0 grams. So I've got grams. I can find moles. We're good at it. But here's what I imagine some of you who got the wrong answer did. Remember, it's 1 mole of N2. Remember, nitrogen is one of the 7 diatomic elements. It weighs 28.01 grams. And that number equals 1.49 moles. Okay. Now, those of you that just divided by the 14, because that's the weight of N, again, you got to pay attention to that. It's one of those 7. Okay. So I'm going to plug in my numbers. I've got 1.49 moles. My gas constant is 0.0821 liter dot ATM Kelvin dot moles. Okay. Times the temperature, which is 100 degrees Celsius, which is 373 K. All that divided by 2.080 atmospheres. And when you work that out, you get, as I said right up there, 23.0 liters. Right? Okay. So again, hopefully these are working out. Not too bad once you get going. Let's try one more. Again, like last time, go ahead, pause the video, try to do this problem all by yourself, and see if you get the right answer. Okay, how'd you do? Is your temperature, does it equal 362 K? I hope so. All right, let me show you how I would do it. First of all, I've rearranged Pivnert to equal PV over NR. Oops, not a very good N. NR. All right. Put my pressure, 318 kPa, times the volume, which is 21.5 liters, times my number of moles. Ooh, I have 100 grams. Well, 100 grams of CO2. Okay. And 1 mole of CO2 is 44.0 grams. Oops. Which I don't have calculated, so just 1 second here. Okay, and that equals 2.27 moles. Okay, so I'll put that here, 2.27 moles. And then times my gas constant, which is 8.31 liter dot K pa over K times mole. Alright, so work that out, and hopefully you get 362 K. Alright, there you go. So a little bit of ideal gas law, I like to call Pivnert. Don't forget the things that are important. We're making some assumptions along with KM theory about these gases. And again, if you have any trouble with these, come see me and we'll practice some more. Hope you enjoyed it.